Okay, so in the last video, we were talking about boiling points, and I told you we're going to continue this conversation with this video, and this is where we left off. So octane, 4-methylheptane, 2,2,4-trimethylpentane. All of those are organic alkanes, and one is straight chain, one is one branched, and the other one has multiple branches. And as you look at the boiling point, it goes down and down, depending on the number of branches that we have. All right, so we said that all of this was due to induced dipole-dipole interactions. So the induced dipole and induced dipole on another molecule really is the glue that holds these particular things together. So I told you that wasn't the only type of force, though, didn't I? So now we need to go through and we need to look at some of these other functional groups that we talked about in our previous videos, and we need to bring those into the boiling point conversation as well. So we had OH groups, and we had NH2 groups, and we had an ROR group, and we also had a halogen. So these were the four groups that we learned how to name already, hopefully at this point. And we also need to talk about how they play a role in the boiling point as well. So boiling point trends also happen with these particular types of functional groups. The ethers, the alkyl halides, the alcohols, the amines, they really all do play a role in boiling point. But in these molecules, they're a little different. And the reason is because these all have a full polar bond. This is not like an alkane, right? So, for instance, with the OH group, on the oxygen, we have these free sets of electrons. Those electrons are negative, and that makes this a very negative area of the molecule. So, no longer do we have to rely on induced dipole interactions to take place, because now we are really starting to talk about charges. The nitrogen's the same way. We have 3 bonds to nitrogen and a set of electrons that's on nitrogen to fulfill the octet. So there's a set of electrons. Those electrons are not equally shared. Therefore, those are negative areas of those particular compounds whenever they show up. The ROR, the ether, as you can expect, you have 2 sets of electrons on those oxygens as well. And for the same reason, we have a negative area now that clusters together. And this is going to be a polar area that's going to carry with it even partial charges. That's all that matters. I mean, alkanes didn't even carry partial charges, did they? And then finally with the halogens, the same story. We have 1 bond, and then there's 3 sets of electrons that make it all add up to 8. All right, so that's even more polar than some of the others because there's more electrons and more negative charges around that atom. So in these molecules, we have polar areas that play a factor in the boiling points. Even if they're partial, they don't have to be full-blown. Even if they're partial charges, they bring something to the picture that a regular alkane does not. So these are not random forces that we have here. These truly are what we call dipole-dipole interaction. There's no induced part of it. All right? Induced dipole is just random chance and then a domino effect happens. These are not induced. These are just straight up front dipoles. We have areas that have polarity that are associated with them. All right? So, here's the story. The more polar the bond, the more glue due to the forces that hold them together, and the higher boiling point that we will see in these particular types of compounds. Dipole-dipole are stronger, as you can imagine, than the van der Waals. Remember that grouping that includes the induced dipoles. They are stronger, and one of the reasons, of course, is because they are partial or full-blown charged. That's just the way that it is. Now, let's rank them. Let's talk about how these really play an order here. Let's first talk about ethers. Okay, so with ethers, ROR. Ethers have higher boiling points than alkanes. Okay, we know that. We expect that, right? And the reason is because of those sets of electrons that are right here. So, ethers rely on induced dipole interactions. That never goes away, folks. I mean, that always plays a factor. I mean, ethers, I know that we have full-blown negative areas at this point, but those electrons still move around. Those electrons can still become lopsided. And if they do become lopsided, then we have an induced dipole that begins to get formed. So that never goes away. Everything really has induced dipole, whether you realize that or not. That is a force that it brings to the table. And when I talk about force, I'm not talking about Star Wars, okay? Maybe organic would be a little bit better if it did. So these induced dipoles are present, but also a dipole-dipole interaction is present as well. So they do rely on both. And because of that, ethers have higher boiling points than alkanes, as long as we're talking about the same formula weight here. Okay, I don't want to get too crazy. I don't want to kind of bring something out that's really tiny and something out that's extremely huge and then say compare when one's an ether and one's an alkane. We're going to keep the magnitude of the carbons and the hydrogens and stuff pretty close when we begin to compare these, whether it's on a test or on a Blackboard assignment and so forth. All right. So ethers have induced dipole going for them, and they also have dipole-dipole interactions. Once more, maybe I didn't clear that up too well up here. The dipole-dipole interaction, you know, here's an ether group. There we go. This is a full-blown negative here in the center. I see two sets of electrons that's going to be there. And then if I have another ether group, something very similar is going to happen here. So this is a negative area. That is a negative area. That also makes this a positive area and a slight positive area. And this attraction between the negative and the positive piece, that is what we refer to as the dipole-dipole bond. That is the glue that holds them together. All right? Now let's talk about alcohols. Alcohols. Okay, so alcohols, well, they have higher boiling points as well. And they also have higher boiling points than ethers, and they have higher boiling points than alkanes. Well, we have to talk about why. Well, here's the reason why. In the field of alcohols, all right, they do the induced dipole-dipole interactions. That is what they do. They all do it, so that's also included. Alcohols also have a kind of a negative area around that oxygen like ethers did, right? Very similar to an ether group. So the dipole-dipole interactions also exist with this functional group as well. But there's an additional one here that ether does not have, and this is called a hydrogen bond. So what is a hydrogen bond? Well, by full definition, a hydrogen bond means a hydrogen that is attached to an N, O, or F. It's got to be one of those three. So an H is attached to an N, O, or F. And here in the alcohol case it is. Ding, ding, there it is. And that hydrogen is attracted to an N, O, or F on another molecule. Okay, so let's kind of draw out an example. Let's say I have methanol. So this is CH3OH, right? And then another CH3OH that's in that mix as well. Well, this hydrogen is attached to an N, an O, or an F, isn't it? Well, all alcohols are. Doesn't matter. They all will be. So that hydrogen meets the first half of the definition on an N, O, or F. Well, the second half of the definition says that it's attracted to another N, O, or F on another molecule. So if we just have methanol and there's another methanol molecule that's swimming around with this one, then that hydrogen, because it's slightly positive, this is slightly negative, we see some polarity here, will be attracted to this oxygen because this is slightly negative, isn't it? Slightly positive, slightly negative, there's an attraction. This attraction is what we call a hydrogen bond. It is not in reference to this one. That is not what we're talking about. A hydrogen bond is not referring to the hydrogen directly attaching to another atom. That is not what this definition is about, and too many people are confused with that. It is in reference to a temporary glue that holds two molecules together. That is what this is about. So it's an H attached to an N, O, or F. That's the first criteria. And then that H has to be attracted to an N, O, or F on another one. All right, let me give you another example. Let's say that we have our methanol again, CH3OH, and we bring this into some water as a solvent. So a whole lot of, one time I was out west and I went through a drive-thru. It was very similar to a Taco Bell. I forgot what it was called, Del Taco or something maybe at the time. They had something on the menu and it was called the Whole Lotta Box. I felt like a glutton when I went through the drive-thru and said, give me the whole lot of box. But here we're going to have a whole lot of water. This whole lot of water, that's the solvent. There's a whole lot of it. And then we have just a few methanols. That's about it. Okay? So the question is hydrogen bonding going to happen here? All right, well, this is a hydrogen attached to an N, O, or F. Ding, ding. That's good. All right? And then that hydrogen can find an N, O, or F from the solvent. It's right there. It's right there in the center. There's my N, O, or F. So because of that, yes, this can participate in a hydrogen bond, and right there's the proof. It meets both sets of definitions. Why did I do this example? To let you know that this doesn't have to be the same. Okay, methanol and water can come together. They're different molecules, and those molecules can form hydrogen bonds between each other. That's not a problem. No one said they had to be the same through and through. They can interact with different molecules if they want to, and here's a prime example. So alcohols have induced dipoles, alcohols have dipole-dipoles, and alcohols also participate in hydrogen bonds. They do all three. And that is the reason that alcohols have greater boiling points than ethers, which have greater boiling points than alkanes. Now you see what we're trying to do here. We're trying to rank these in an order that's something that makes sense, that we can relate to a pattern or a theory. Okay, so there's an example of hydrogen bonding, but you know what, folks? Alcohols are not the only thing that can participate in hydrogen bonds. Look at this other group. Oh, this other group is a nitrogen-containing group that we call an amine, the amines. Well, definition of a hydrogen bond. A H attached to an N, O, or F. Oh, there it is. There's my N. And then that H is going to be attracted to another N, O, or F on another molecule. Well, amines will participate in hydrogen bonding. So the amines, by default, will do induced dipole. That's something that they do. And they also do dipole-dipoles. And that's because we get some free pairs of electrons out here on their own. We get some charge separation that begins to happen, so that's a dipole-dipole. And they also participate in hydrogen bonds just like alcohols do. Okay, well here, this nitrogen has a hydrogen that's there and a hydrogen that's here. There's two hydrogens that are here, two of them. And the tendency here is for people to say, well, there's two hydrogens, so that means it's got to be greater than the alcohols because the alcohols only had one. And you know where I'm leading you with this. Nah, that's wrong. And now you're scratching your head and saying, well, why not? That looks like that would make sense. Nitrogen has two hydrogens on it, possibly, depending on what type of amine it is, primary, secondary, tertiary. But the reason that this does not work, here's the reason. because we're missing a bigger part of the story, right? The bigger part of the story here is that oxygen has a higher electronegativity value than nitrogen does. If you look on the periodic table, it's N, O, and F. That's the order that they come in. That's why I write a hydrogen attached to an N, an O, or an F. And this is the highest electronegativity value. And as we go further away from fluorine, the electronegativity value decreases. So oxygen has more electronegativity than nitrogen does. Therefore, the bonds between the oxygen and the hydrogen, those are actually going to be stronger. Now, I know that kind of sounds weird, but the relationship here is all about charge distribution. And the bigger the charge distribution, the stickier the glue. That's how I want you to interpret that. So if we have a full-blown positive and a negative, that is super sticky glue, all right? But we normally don't have that in organic. We have partials. And here we have a partial positive and a partial negative between O and H. And then we also have a partial positive and a partial negative between N and H. Well, oxygen's more electronegative. Oxygen is more electron greedy, which means that oxygen will end up creating a bond that is a little bit more tackier than the nitrogen and the hydrogen will. And this is why alcohols actually have higher boiling points than the amine groups. So I'm going to come up here and I'm going to erase this. And now we've got to sandwich the amines. Well, the amines are going to be greater than the ethers. The reason is because ethers do not participate in hydrogen bonds. Amines do. And then alcohols are going to be greater than amines. Even though they only have one hydrogen, the charge separation here is much greater. And that charge separation is the glue, that's the stickiness that holds these molecules together. So because of that, those boiling points are going to be higher with the alcohols. Now, with the family of amines, notice what I said, primary, secondary, tertiary, right? So this is representation of a primary amine group. We can also have a secondary amine group. And a secondary amine group is a nitrogen that is attached to maybe two other carbons, right? This is a secondary. Notice that this still participates in hydrogen bonding as well as dipole, as well as induced dipole. Tertiary, though, a little bit problematic. Tertiary is a nitrogen that's connected to three other carbons, and there's no hydrogens here. So a tertiary amine does not have any hydrogen bonds. It cannot participate in hydrogen bonding at all. And the reason is because there's no hydrogens that are there to participate in the hydrogen bonding. So we're still going to keep it simple. I'm still going to put amines in that category, and we're going to say that represents primary, secondary, and tertiary amines. So I'm not going to mess up that order or that ranking on you at all. So alcohols have greater boiling points than amines. Amines have greater boiling points than ethers, and ethers have greater boiling points than alkanes. All right. Okay, so here's an example of the different types of amines that you might see. This is comparing a primary versus a secondary versus a tertiary. A primary amine here is 97 degrees. Here we have a secondary amine because there's a carbon to the left and to the right. So that lowers the boiling point because, again, if we're comparing just amines only, then we have less amount of hydrogen bonding that can take place here. And then tertiary amine, this is all three together connected to the nitrogen. There is no hydrogen bonding that can participate in the amine family, and that boiling point goes even lower because of that. All right. Now, notice what I did. At no point in time have I brought in alkyl halides yet. And I did that for a reason. So, right now at this moment, we have only compared alcohols, amines, ethers, and alkanes with each other, but we have not brought in the halogens yet. And that's what we're going to do in the next video. So I did not leave them out. We're going to talk about them. We're going to figure out how they fit in with this whole discussion with boiling points. And then we'll go back and we'll kind of clean up this description of boiling point and relate it to melting point all at one time. So in the next video, we'll focus on alkyl halides. We'll continue to talk about boiling points. Don't go away from me yet. We're on a roll. It's the same kind of common theme that we're going to be talking about in the next one. So just close this video out and push play on the next one, and you are ready to go. So I'll see you in just a few seconds.